let's do an example of finding a limit numerically and looking at a bit more of a step-by-step procedure for this. So step one is to approximate the left-hand limit by plugging in values into f of x slightly smaller than a itself. So like in the example we did earlier, we were trying to determine the limit if a was at a equals 2 for a parabola and a couple other things. But, you know, for instance, we could say plug in 1 or 1.5, 1.9, 1.99. And usually I would probably recommend starting pretty close to 2 right off the bat. But, you know, it might be easier to start with, say, 0 or 1 just from a numerical standpoint if you're doing it without a calculator especially. And continue to get closer until you are convinced what that limit would be. Again, this is not a proof. This is not a formalized process for unequivocally proving the limit, but again, this will help us determine what the answer needs to be, or what we think it will be. Step 2, approximate the right-hand limit by doing the same thing. Essentially, take values slightly larger than the targeted location, such as if a was 2, we could check 2.1, 2.01, 2.001, getting closer and closer to the value of 2 as well. And then finally, if those limits match, that is most likely your limit. Like say they're both approaching 4. Like on the left-hand side, you get 3.99. On the right-hand side, you get 4.01. Most likely, those are both trending towards 4. And if not, if they are not the same, quite obviously, then the limit does not exist. So let's do a couple examples from the slides, and then we'll move back to the packet. Usually I follow the packet a little bit more closely, but I have some slides that kind of help me introduce the idea, which is why I like to begin with these. So let's say I was trying to find this limit numerically. Actually, let me get out of my slideshow for a second so that I can have access to my calculator. Like let's say I wanted to determine the limit of 1 divided by x squared minus 4x plus 4 numerically. Well, let's say I didn't have a graphing calculator and just was using a scientific calculator. Basically, I could say try plugging in 1.9 or something like that to see what would happen. Like 1 divided by 1.9 squared minus 4 times 1.9 plus 4 and see what that gives me. In this case, it gives me 100. And again, for all I know, that limit could be 100 or 101, or 102. So doing just one test is not a very good idea. I would check at least 3 places to the left of 2 before I was convinced about the right-hand limit. So I might also check, say, 1.99 or 1.999 to see what was happening. And again, this would help me distinguish between, okay, is this headed towards infinity or is this headed towards 100, And so if I check 1.99 instead, and how I did that was if you hit second entry, it will copy your previous line, and then you can just make adjustments to the formula as you go. You can even scroll up and hit enter if you'd like to adjust it without having to retype in the whole function every time. But when I plug in 1.99, that gives me 10,000, and it appears as though this is going to get really, really big. Now, we also need to check the right-hand side before we confirm or guess that this limit is indeed infinity. But we could do the same thing where we check what about 2.1 and what about 2.01. Those are a couple good spots to start with for this particular limit. So I checked a little bit smaller than 2. Now let's check a little bit bigger than 2. Now if I check 2.01, we have 10,000. I skipped over 2.1, but again, there's no exact way of doing this. This is all, you can pick whatever numbers you want. It just is helpful to have a procedural way of getting closer and closer to 2. So then we could even go to 2.001 to see, and it looks like it's 1,000,000. And if you recall, I did the same exact process using the graphing calculator trace feature, which is a way of kind of simultaneously doing both this sort of procedure and looking at the graph at the same time, and it can be easier to come up with a solution. Now let's say we wanted to check the limit towards 0 of 1 over x, which we have already stated to be this does not exist from a previous video. But again, we could check a little bit to the left of 0, so say negative 0.01. And when you're at 0, you want to make sure you just checking negatives and positives. But if I did 1 divided by negative 0.01, that would be negative 100, and 1 divided by negative 0.001. So again, I want to get closer and closer to 0 from the left-hand side, and what I can see is those are getting increasingly large and negative. And my guess here would be, again, probably headed towards negative infinity. And if I'm checking from the right-hand side, again, that would just be to the right of 0, which would be positive, and again, getting increasingly small. So 1 divided by 0.01, 1 divided by 0.0001. It appears as though this, as we've already looked at graphically, would head towards infinity as well, because it is growing in an unrestricted fashion. So, but just to reiterate, the left-handed limit was headed towards minus infinity. The right-handed limit was headed towards positive infinity. Those did not agree, so this one, we would say, this one does not exist, whereas this limit was headed towards infinity. And similarly, we could check functions like, let's say, looking at the natural log. This is a limit that can be quite tricky, but if we wanted to check the limit towards 0, technically, we could look at it from the right-hand side, because the limit towards the natural logs, if you recall, are undefined for negative numbers. Like if I was to try to do the natural log of -1, my calculator would most likely tell me that this is an error. Actually, depending on the mode of your calculator, you can actually take logarithms of negative numbers, but we're not going to worry about those right now. We'll talk more about exponentials and logarithms in a later chapter. But for now, if we wanted to check the log from the left-hand side, sometimes you might not have a left-handed limit. Like in the case of a logarithm, we can't try plugging in values to the left of 0, because every time it gives us an error. But what if we look at the right-hand limit instead, which actually does exist? But let's just say we were checking it from the right-hand side. Like say we started with 1, which is a little bit to the right of 0. The log, if you remember, the log of any base of 1 is always 0. But we could see what would happen as we plugged in slightly smaller, like what about the log of 0.1 or the natural log of 0.01 and so forth. And what we can see is that it is getting larger and negative. And the question would be, well, is this reaching a particular limiting value, or would this be negative infinity? And in this case, I would probably want to go a little bit further before I came to a determination if I was using this numerical method. And it seems as though it is unrestricted. And because it's a logarithm, you might notice a pattern with the decreasing nature of these particular values here. But if if you're not really sure if it's going to head towards infinity or level out, you could just continue plugging in larger, or in this case, smaller and smaller numbers, closer and closer to 0, until you can say, well, this is probably minus infinity. And technically, when it comes to the natural logarithm, if we look at a graph of the natural logarithm of x, what it sort of looks like is this curve is going down here and sort of stopping or connecting. It sort of might look like it has a y-intercept on the axis, but this function actually has a vertical asymptote. It heads down towards minus infinity on the right-hand side. Though, again, since it has no left-handed limit, we'd say that this limit does not exist, though the right-hand limit does exist and is indeed negative infinity, even though it doesn't necessarily look like it sometimes with a graphing calculator. You can't always be certain, and this is why you have to take certain methods with a grain of salt, such as graphical and numerical methods. Sometimes it might look like one thing, but that may not be the case, which is why I always recommend trying multiple different methods, especially for these trickier examples.